So Danijela's last lecture.
So last time I said it was the business to centralize is the centralizer zero R. That's not right. We actually do a bit more. So we actually classify the centralizer for any small division. Because providing support in those divisions. We can tell what if it's not very hard. So in this example, we visualize it. The centralizer left. There are three possibilities. It could be B, it could be B plus C, or it could be B squared plus C, in which case, centralized classification as well. But I want to first go back to the global review. There's something I want to say, which is kind of a general thing. And then I will talk about global rigidity, conjecture, and results on general manifold. And I'll give you something that we conduct in the semi-manifold. Okay. So let me explain this. This is kind of important. And I'll do it. I'll do it actually by repeating what we've done before. But I'll do it faster because now you already know everything of the cycle. So we are now again back to our toy example AB. So I'm commenting this. This is like a remark. We'll actually prove that. And instead of taking the isometric potential extension, so taking isometric extension, take a hyperbolic potential extension. So take F to be defined like this. AX, B1, AX, let's take the same, AY plus 5 of X, and take G, and that's Y to be BX, BY plus 5 of X. So now, volume side, function from 3 into R3, new function. And I want to repeat the same procedure that I did before. So if they switch a move, I can easily compute and get a relation much like the one I had before, which was called double star. But now it will look like A psi minus psi composed with A, B phi minus phi composed with B. Very simple, right? So now I have the three joint eigendirections for MD. Let's split this equation because this is a R3 diagram. Let's split it. So split into eigendirections. Split equation. second direction. Right. And then just so as not to drag indices around, what we get is eigenvalue of this times some real value function. Let's not write indices. Okay. Minus psi composed with A, and 5, and 5 composed with B. Well, now psi and 5 are some real value functions. So much like the equation we had before, except that now these guys are not of absolute value 1. Okay? So if you have ever went through the structural stability proof for the automorphism, hyperbolic automorphism course, you will find that this looks familiar. This is kind of the equation you need to solve. You find the zero solution because this is not 1 or not correct. So how does this work? Exactly like we did before. So solving a single equation. Solving the single equation. A single equation will look like phi equals same as before. Lambda h minus h composed with a, with a big difference that now I have this lambda here. So this equation has zero solution. Actually, not solution. One is let's call it 1 to 4. B plus k is going to be a sum. K goes from 0 to infinity. Lambda to the minus 1.1. And 5 composed with a to the 2. That if lambda is bigger than 1, we use this because then this is 0. Then if it's less than 1, we take negative stuff. And because this lambda is less than 1, we can sum this up and show that these are actually 0. This is the classical thing you would do if you were to solve stability for the hyperbolic automorphism. Oh, because is negative. Yeah. Right. So now we look at what this equation gives us. This equation actually gives us from this one. This is the double star. So this double star equation gives us that I will skip this to calculation, of course, every time, but we can pretty easily go through with it and see that these things you can also write through the data. So these things will be equal. This is exercise. Show that dA plus minus is equal to dB plus minus whenever they are 0. So now the point is, what do I get from this? Remember that what do I get from this? Okay. That's all this picture, yeah. Perfect. Let's keep it alive. So now assume still remarking on the theory.
And when you wrote solving phi equals lambda h, that's a different phi than the phi in star star. So it'll be helpful, but you haven't told us why. Okay.
What is when this is? So I feel now that I have F here, homotopy. And assume that F is a number. Then you all know that from Katok-Spatzier, you actually have a homeo from S to A. Okay? And the whole point is to follow this homeo to that system. So when you have a general action like this, of course, I can do the same as I did here if I have an Malian method, and I have it. I can take the Malian method to that with this folder. This is not only folder, it is folder and not important. And you can use the operator decomposition for an abelian action. Operator decomposition for abelian action. Will tell you that if you have a DK RK action on M, we will measure mu and important general thing. Then there is this measurable squeezing of the tangent bundle into measurable fluid spaces and measurable. And I have finally been functional psi I from my group. So whatever is in right in the case into R and functional to my functional. Like we had before, we said that now everything is measurable. Such that psi I of A is exactly the Lyapunov exponent of A in EI. The same because the normal example because now you have a decomposition between variance under the action.
You want that measure ergodic.
Yes. Action measure ergodic.
And did you say that mu is going to be the push forward of Lebesgue measure under H, for example? Mm-hmm.
So what this gives you, we can draw the same function before. Now I can still draw this function description. If I was in three, maybe I have 3 lines, 2, I don't know. But these will still be turned out at this point. And because now, the thing is that if you have positive proportional components, of course, you get the same one, and negative. So it's very useful to actually group the into something that's called force. And force direction. EI. Sum of EI. Where this goes to either all psi I, which are positively proportional to psi, so that the same wall. And it's the same wall, this is the same positive negative. And both C is positive. This is called force. Conjecture for distribution. And it's measurable. Doesn't measure. The next is when you assume that you have some but if I assume that an element is here and open. There's this A and also I have this the integration of the tangent rate into this form, into this, sorry, not into this, into a select. Put something like this. This integration. So everything is measurable this one. But now we have a natural. It is a natural element we force the splitting here into two pieces. One will be stable for A, and one will be unstable for A. And because there is a Anosov, I know that these two are folders. Now, what doesn't tell me much? Doesn't the actual sort of in a folder way doesn't see any of these people that level. But if I have one more element of the actual the C is also. Then you have a different treatment. Maybe this is stable for B, and this is maybe stable for B, and this is maybe unstable for B.
When you write W, you mean like E, the bundles.
That's the folder formation. No, correct. So these are folders into the folder formation. So now if you have two on two sides of the wild chamber wall, then whatever intersections we have are going to be folders, and they are going to integrate the folder formation with the just intersection of stable and unstable within that result. You get a finer, significantly finer division into folder space. For one, and it will be folder. Then maybe this will be some. Also folder. And so on. So you get the picture. The thing is that initially these things are just measurable. But if I assume enough elements, enough Anosov elements, because if I assume one Anosov is stable, I can actually get that these measurable distributions are tangent to folder formation. And then they will be almost everywhere. So this is a proposition. I don't know. It's not possible. Proposition. One and also in each chamber implies that the coarse diagonals are folder integrating to folder foliation. So that's why one and also each chamber is really good thing to have, because then you have this fine, this much finer division in the folder than the initial have for a single one. Now we go back here. So here I managed to produce 0 solutions, but I have more. So the two-star equation actually gave me that these two must be the same. So now let's look at our picture for say the FG action, the one I just drew there. And suppose that, of course, I can do plus minus like I did before, so it's finally contracting. So plus, minus, plus, for example, here, and suppose my A is here. This A is this capital A. This capital A. Suppose, so then to solve this equation, let's fix that I'm solving this equation in direction V1. So let's fix it here in direction V1. So in V1, lambda is going to be positive, either the one, so this one is going to be positive. And I will use the dA plus form. So when I use the dA plus form, I look here and I see that this is going to be less than 1. So if I differentiate it, I will be able to differentiate in any stable direction for anything. So my solution, let's call it this H that I'm trying to prove, is actually 2. So H is V infinity in direction V2. In direction V2. It's not in V3. Then if I have one more element, but in different Cloud chamber, where I have plus, minus, minus, then I have that H is actually D plus B, and when I look at what should be D plus B, it will be similar somewhere here, and then I will be able to differentiate this table for B. I get one more direction. Infinity in V2 and V1. And what happens then? You go down.
V2 and V1 are the stable directions for V2 and V3.
V1, V2, V3. The two stable directions between. So it seems like I get more when I go down. But in fact, you can get all the directions like this because of generalization. Then like I mentioned together. The one direction you cannot get is the V1. You can do this exercise for example. Do this exercise and you will see that you can get the direction V2, V3 always, but not V1. So now if I want to differentiate in V1, if I want to differentiate in V1, I have a problem. Because this is lambda, this is lambda 1, this is the eigenvalue in the direction V1. So I differentiate in this direction, and I kill this. And I don't have a contraction when I don't kill. So that's the problem. But not so big if you have a total Anosov selection. What happens if you have a total Anosov selection? So it's not only one in each chamber, but everybody is Anosov. And you have this Anosov element getting close to the wall as much as you want. What happens is that instead of picking A in the middle, I can pick A somewhere really close to the wall. So that if lambda 1, if this is the wall L1, kernel phi 1, so that the lambda 1 here is going to be really small. So small that the exponential mixing of which I was talking about before kills it. So that it's much smaller than what I get from exponential mixing. So if A is chosen close to the wall, then exponential mixing gives us that gives us that this full sum lambda 1 minus k plus 1 5 equals to a to the k, where k goes from minus infinity to infinity is 0 as a distribution. So what does it mean? I can do the same trick I did before. I can use positive or negative, and I get movement into V1 direction. So this is like before. That H is infinity in the V1 direction as well. And you get movement. So that's a two-way game that we play here. We base with AB and with a cosine with the hyperbolic. Now imagine if you have a general action,
Wait, before. In this example with these file chambers, it's the chamber picture of it is telling us we can't do V1. What is it about the first entry? Like, why is it not enough just to have like an Anosov C, D, one in every chamber? What goes wrong? Uh-huh.
no matter how you define the double star equation is not. So well, good question. That's what I was talking about next. So this is the algebraic case. This is really the algebraic. I mean, what I did here is the exponential matrix for AP. Now, I want to say that in this theorem, actually, how the proof of this theorem goes. You have something which is polar conjugate to AP. You have an action which is polar conjugate to AP. So how the proof of this theorem goes is that we take you assume only one of them.
So what are we proving right now? The to global rigidity for theorem 2?
Of course, there's one part which I don't have time to explain, but how this applies. Theorem. How this applies? Well, here you have FG. That which actually was the one step in chronological topology proof. But the first step nowadays would be to show that one Anosov implies one Anosov in each chamber. And this is difficult and years pass until this is proven by this is already effect one. And I'm not talking about it. Now, once you have one and also in each chamber, then the fact that you have polar conjugacy allows the proof that actually Anosov elements in the essence are then. So this comes from the fact that we have polar conjugacy. And this is in paper by
And you mean projectively dense here?
this is also very correct.
It's a lattice.
Actually, even more, everybody. And they also use this sort of function, so the wild chamber pictures of the nonlinear and the linear side, that's it. Wild chamber picture. Same. For FG and A. So now you have a total Anosov action, Anosovs are then going to the wall, and then you play this game that I told you now. So then you say, unfold a conjugate to an exponential infinity. Put it exponential increase for folder available. And then you play the same game. Then use exponential mixing argument on this is now totally unnatural. So you can have it, I don't know, call it totally unnatural fix. Totally unnatural fix, because you have close enough to the walls, then you can reduce this natural. So that's the plan. Now, exactly. But the same same as we do for any of the that's very good point. The same chamber. Exactly. So once you show that you have one and also the one chamber, then these guys integrate the folder formation to their folder, and this doesn't depend on the method. There's no method yet. This is the same for any one another. So that's the key thing this often. Okay. Now I want to show you, or I think not to show, but maybe what happens here in the semi-local case. In the semi-local case, let's go back. So we start with a map which is like this. So we have a fiber partially hyperbolic system over source. And the fiber is one-dimensional. And some of our map acting on the fiber system, the map F0. The map F0. Now, F is the fiber partial hyperbolic system. If you fulfill this, you're again going to see a fiber partial hyperbolic system as a over and for F.
That's Hirsch-Shube, actually.
But what you get for what you have for F0, you have manifold, fiber manifold, factors to the source to C. And if you have F, you will see a vibration by central value. And this vibration will be topology. This is topology. And in the base, I will see some map. And this map will be topological enough. So the thing is that if you're close enough to F0, quite equal, and so you will actually get a digit folder. If this map in the base can be sufficiently big centralizer, it can be good. Then in the base, what you see is something that looks topologically like AB. This looks topologically AB. Then you have folder vibration, and then you have your action of the centralizer on F of all T. So the idea is that in this case, we can draw the one chamber picture for Z of S. And it will be, in fact, we show it will be looking like that. Exactly the same as the wild chamber picture. Moreover, we start with only one partially hyperbolic lattice. But in fact, we can show that not only one, but actually everybody who is everybody in this chamber is partially. And then the key thing that we do to show the rigidity part.
And just to be clear, that those chambers are for the hyperbolic directions of the partially hyperbolic. So
I should say something I was saying in the beginning, but so here you have initially the centralizer commute and everybody has this one. So for the unperturbed map, remember that you also have some direction with zero. But it doesn't, for this part of the statement, it doesn't. So the base will be the hyperbolic on the base, the super hyperbolic, the strongest Anosov in the base. And can be linked with so that, but then you see here that actually we actually get complete classification. So this part of the result is why we need volume preserving. Because in this part of the result, we use the dichotomy by for the volume disintegration along the central V. In this part, to get this is volume disintegration like Wilkinson. You start that, and I will do it using, I will do taking, and I will say what, I want to say something else. We take a volume, we disintegrate the one that is to the center. What it is that if S is acceptable, then one is two possible situations. Either this disintegration is atomic, or it is very nice to go. If it's atomic, then you can imagine that if you can look at some atoms, we can show the volume of the like and of the light. If it's some atoms, you must remove them. But Disheng will talk more about this. And I want to actually tell you about global rigidity on general. You see, this was global rigidity. I use the manifold, the new manifold, the homogeneous. However, the Katok-Spatzier actually, after the big stack of local rigidity, they stated the following conjecture, which is completely global. So Katok-Spatzier conjecture said the following. So if a DK from RL and on a smooth compact manifold K plus L contains an Anosov element and has no random function. Then actually mostly algebraic. Maybe modular finite factors. Yeah. Modular finite. So that's the conjecture. Now, the way they say, you see how much trouble even when you knew it's not so real. Even when you knew that you had to make the thing. So this is crazy because that the homogeneous structures appear out of nowhere. Where we go? So in the conjecture state is in fact is wrong. This is why there are no results. But as you stated, this is wrong because there is a recent counterexample. Yeah. It could be, but it's just, yeah, it could be also the function. That's also not the best. Yeah. But it's just one possibility.
So algebraic, you mean affine, as you were saying before,
It could be a bihomogeneous.
or it could be bihomogeneous.
Counterexample. It's beautiful vintage. Very beautiful, very nice. What it does make the sign change of the example. To be. Sign change of the product of an Anosov. Sign change. Full sign change. Small sign change of example 2D, which is the product of given flow or any Anosov flow. Which has no one around factor is an option and not of the right, not smooth of the right. So the conjecture is not correct whenever what? It's not actually algebraic. It's not algebraic.
Not C0 algebraic. That was the question.
So Katok-Spatzier conjecture.
And does it have an Anosov in every chamber? Okay. It does, but it's not totally Anosov.
Yes, conjecture. That could be true. Okay. And the thing is that There are essentially no results on manifolds which are not manifolds with one element. But there are results, several results, when we assume topology. So you can say a modification would be a modification, of course, we still survive with decay, but a modification for RL, if you want, modify would be to assume totally also. And there are results. So when you have total analysis, there is a theorem, very nice, beautiful result. And also introducing new techniques for creating these structures by Danijela. I will not say this exactly, because I will not have time to say much about it. But I just want to say that if global rigidity on any manifold to produce homogeneous properties of the homogeneous action, providing or RK, providing total responses and one more really important solution for them is that it's force output distribution, distribution. So these are distributions I have in their board earlier are one dimension. And of course, triangle. Okay, we have kind of a follow-up in some sense, you can say. So they introduced a method where, so this property, as we triangle, remember that in the first lecture I said, if you have no measurable work factor, then every line will act vertically. If it acts vertically, say with respect to volume, then we get resistivity. So these actions of these lines will come back, and this helps to build up this homogeneous structures on the course in direction because they are one dimension. And because you're in the general manifold, what you do with them? If they are not smooth, otherwise you can just take the bracket and build a homogeneous structure. What they do, they make a three products of the two, and then they use sort of kind of like the psychology. It's very complicated, but to show that you actually get a group structure. Three products of this direction, all the groups that you get from different directions, factories by using the action, and you actually get a group action in the four manifolds, and that is the homogeneous action in the manifold. This is really short what they do. They introduce a new method of building homogeneous structures. And there is something we proved together with them, Disheng and I, also global. So, Spatzier, then have two A global rigidity results. I will not say this. I don't have time. I have time. I have time. So you take an RK action, totally Anosov. And one assumes several things. So assume that the hyperplanes in the world in the system X transitively, support the transitively, has them body. So assume that there exists an accessible element in each one of the wells in the wall. Wells in the wall are accessible. This is a super accessibility. Like what we had in example 3D of the wells in the zone of the Diff. Those walls are accessible. We assume that the oscillating decomposition is so nice that in intracellular space you have a measurable method which tells you exactly how you're trying to by the student of movement. So we call it oscillated measurable conformal. Oscillated decomposition is measurable conformal. So in this case you get simply algebraic. And here, the bi-homogeneous situation can appear, like here. And also, here the Corsi elements do not have to one another. Because the possibility is needed for the definite various principle. Okay. That's about global distribution. Now I will draw to tell you about things that we believe we can, in this way we can generalize this and postulate this. Similar results is much more general. So conjecture, conjecture, which we can call like fibers Katok-Spatzier or extended Katok-Spatzier. We didn't really talk much about it because I think it was not so things has to be now not an author.
Depends on whose conjecture this is. We didn't say whose conjecture it is. So whether I object or not, it depends.
And then everybody says, oh, this is conjecture, this is not. So I would like to say, take the fiber partial hyperbolic. It's like extending to the fiber. Fiber partial hyperbolic system and assume that the centralizer contains a three-dimensional contains a three-dimensional subgroup of maps which are identical with base, meaning this is a fiber system by plane where K is exactly the dimension of the center. So if the base is topological, if the base centralizer F is would be projected to the base. Projected to the base is has no zero around the object or measurable. If you want to make it more like this, 9.5. Then F is a smooth algebraic. No, F is the smooth vibration over smooth algebraic. Over algebraic. Smooth algebraic.
Yeah, I think when you say that it contains a k-dimensional subgroup, you want to be more precise, yeah. That it contains like a C0 closed Lie subgroup, a Lie group. I worry. I worry about Katie's example. Maybe it's okay.
Okay, we can discuss.
Okay.
Right, this is over, but I want to say something about I mean, this is actually what we did discuss. Definitely discuss. You said we think about two position vector interesting.
You have 2 minutes.
So, assume F0 using that on homogeneous space, so this is just what this is. Assume that this is an algebraic formula.
Connected.
And assume now I will write something and then I will tell you the equivalent of something if you want. Stable of F0. This is a subgroup in this unstable of F0. A subgroup, they generate a group. Take a lattice, take a closure. This is supposed to be G. So Disheng will explain what this is. He'll explain what this means. This is deciding a testable example, like single element of the wild chemical. It's also describing ergodical automorphisms. So then this is critical. So this all falls into this. And this is actually equivalent, proven by Dani, that F0 is K. So that's the setup. And then F is P1 small perturbation of F0. And then we progress to the following. And then the other outline. So also, but also, yeah. Zero has no conductor. Zero It's actually isomorphic, equivalent, and simplifying. It's even weaker. I mean, it's even less. Here, hyperbolized property. And we select below. And here that also has the random factor. Then simplify. It's like a trailer. Different communities, so you trailer before X equals everything. So we'll speak about why before and second integration.
Thank you, Danijela. We're slightly over time, but if there are any questions, since it's her last lecture. Well, so the question, let me repeat the question. So there's kind of a well-known question whether every Anosov diffeomorphism must be supported on a nil manifold, in which case it would be topologically affine. And so the question is, Katok-Spatzier would say if you have F and G commuting higher rank Anosov, one of them Anosov, then your manifold would have to be also a nil manifold. And the question is that, would you expect that to be easier? All right, any other questions? All right, let's thank Danijela again.